Pre-lecture video, Drawing Lewis Structures. Lewis structures represent the connectivity between atoms. They represent the covalent bonds used in molecular compounds and help us visualize how the octet rule is satisfied for all atoms. For simple homonuclear diatomic elements, Lewis dot symbols can be paired together. In molecular chlorine, we can take the dot symbol for one chlorine atom with 7 valence electrons and a second chlorine atom with 7 valence electrons, then take the lone dots and share them in a bond to make chlorine with completed octets for each atom. In nitrogen, we can take the Lewis structure for 2 nitrogen atoms, which have 5 valence electrons each, and connect 3 of these valence electrons to complete the octet for nitrogen. This system of each atom contributing the exact number of electrons to the structure does not always work well, however, especially in cases where ions or multiple bonds are formed. Instead, we can consider distributing all of the total valence electrons to all atoms in a way that creates the most stable molecule. To do this, we follow the rules of 1. Getting a total valence electron count. 2. Establishing a central atom, which is usually the least electronegative atom and often the first atom listed in the chemical formula. 3. Bonding the central atom individually with each of the outer atoms. 4. Putting electron lone pairs on outer atoms to complete their octets. And 5. Placing any remaining electrons in pairs on the central atom. In certain cases, if the central atom does not have an octet, we'll move lone pairs from the outer atom into multiple bonds. Let's take a look at an example. Dichloromethane is a common solvent for organic chemistry. To get a total valence electron count, we need the formula of the compound CH2Cl2. Carbon provides 4 valence electrons, each of the 2 hydrogen atoms provides 1 valence electron, and each of the 2 chlorine atoms provides 7 electrons for a total of 20 valence electrons. Then we create the structure of the molecule by placing carbon in the center. Note that it is the least electronegative atom except for hydrogen and is the first atom listed in the formula. And we connect each of the outer atoms with a bond. This uses up 2, 4, 6, 8 electrons, so subtracting 8 electrons from the total valence electron count gives 12 electrons we have left to distribute. Finally, we add lone pairs to complete the octets on our outer atoms. Since hydrogen already has its duet filled, we just need to add lone pairs to chlorine. So we add 2, 4, 6, 8, 10, 12 electrons, 3 additional lone pairs on each outer atom to complete this structure. This looks like a completed structure, so we can count to ensure that we have used all 20 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 total electrons that are visible in our structure. To check our structure, we should ensure that all of the atoms have the appropriate octets or duets. In this case, we end up recounting shared electrons. Let's start with the chlorine atoms. One chlorine atom has 2 shared electrons in the bond and 6 lone electrons, or 3 lone pairs, for a total of 8 electrons, fulfilling the octet rule for this chlorine atom. Looking at the other chlorine atom, it also has 2 shared electrons in the single bond and 6 lone electrons in 3 lone pairs, so it has a completed octet as well. Hydrogen, being an exception, requires only 2 electrons, so its duet rule is fulfilled by the 2 electrons shared in this bond. This is the same for the other hydrogen atom as well. Finally, the carbon atom has a completed octet because it has 8 shared electrons in 4 bonds. So each of our atoms has a completed octet or duet rule, and so all of our rules are satisfied. Let's take a look at another molecule. For sulfur difluoride, the formula gives us 6 valence electrons from sulfur and 2 times 7 or 14 valence electrons from the fluorine atoms for a total of 20 valence electrons. We set up the structure of the molecule with sulfur in the center and use up 4 electrons in each of the bonds. Completing the outer octets by adding 3 lone pairs for each fluorine atom uses up another 12 electrons. Finally, the remaining 4 electrons go in pairs on the central sulfur atom, and that uses up all of our valence electrons, and we can ensure that fluorine has an octet, 3 lone pairs and 1 bond, and that sulfur has an octet, 2 lone pairs and 2 bonds. For carbon dioxide, which has a total of 16 valence electrons, we can quickly establish the backbone structure with carbon in the center, but when we allocate electrons to complete the octets on the outer atoms, we will be out of electrons. Clearly, the carbon in the center does not have a completed octet. Since we have no more valence electrons, we can't add electrons, nor can we take away any extra electrons. Instead, we'll move 1 lone pair from one outer atom and use both of these electrons in a double bond, and we'll do the same thing for the other outer atom. With the final structure, then, we have completed octets for all of our atoms, and we haven't changed the number of total valence electrons. We've just rearranged their positions. Finally, we can prove that this system works even for the diatomic elements that we saw earlier. For molecular nitrogen, we have 10 valence electrons, 5 from each nitrogen atom. We can arbitrarily choose one of our atoms as the central atom and create a bond, then complete the octets on our outer atoms, or in this case, the octet on our outer single atom. The 2 remaining valence electrons go onto the central nitrogen atom, but then we're out of electrons. So, we redistribute electrons by moving 2 lone pairs into bonds, and we establish the nitrogen-nitrogen triple bond without adding or removing electrons. When you have completed your structures, be sure to do a total electron count to ensure that you've used up the correct number of valence electrons, and also be sure to check for completed octets on all atoms.